Welcome back, it's True again with another Cafe Yocto episode featuring the phyCORE-AM62x System on Module and Development Kit. Today's video we're going to be talking about building the BSP, or specifically the Linux board support package. Now what's a Linux board support package? That is everything you need to boot your System on Module into Linux. That includes your bootloader, the Linux kernel itself, and then the root file system that's going to contain the kernel modules, libraries, other packages like Python, user space applications, and specifically application software unique to your custom application of the song. The way we build these BSPs is using the Yocto Project. That's like a great build tool. It's itself consisting of a bunch of other tools. It's like a collaboration project. It's all open source and enables us to bake and build everything into a production-ready image. So a single binary file that you can flash directly to disk. And what I mean by production-ready software is you don't want to deploy a system out in the field and have it rely on network connectivity or user intervention to set itself up, right? So production-ready software image would be you have essentially all the dependencies, all the software is all set up by default. It's baked in. And so that's what production-ready software is. And that's what the Yocto Project enables us to do. So getting started with that, in order to build with the Yocto Project, we're going to need a number of things. For our phytech BSP specifically, Alpha 1 at the time of recording for the phyCORE-AM62x, you're gonna absolutely need this specific Ubuntu distro that we recommend here, Ubuntu 18.04 for Alpha 1. The reason is because it really comes down to how much support you're going to need. You can use pretty much any Linux host machine, I think, for building with Yocto. However, in order to satisfy the build dependencies of the board support package itself, there might be a lot of workarounds. You might need a lot of support, and depending on that level of support, phytech is just too resource constrained when it comes to our support portal. So we recommend just going with what we actually use to validate the BSP. This will just make your life a lot easier. So go with Ubuntu 18.04. You're going to need root permissions. And you can get that set up in a number of ways. Native boot, you could host in a virtual machine. That's how I do it. You're going to see me use VMware Workstation here in a bit. When you set up that Linux host machine, you're going to need at least 200 gigabytes of disk space to house all the sources and then, of course, the deployed binaries of the BSP. You're going to need 8 gigs of RAM and 4 processing cores at the bare minimum. Really, you're going to have a terrible time and a horrible life if you operate with these bare minimum recommendations. You want as much RAM and as many processing cores as you can get. And then because the Linux board support package relies on so many open source components, you have to have an active internet connection to download those open source components from the internet. Okay, let's get into these actual steps, and I'm going to introduce my VMware Workstation Ubuntu 22, if you notice. That is not what I recommended just a bit ago, right? Well, what I do personally, just to explain, because the vigilant will notice this, I always run the latest Ubuntu locally in a VM, and I SSH a cloud-based build server with dedicated build resources, tons of processing cores, lots of RAM, and that's hosted like in another part of the building, and the IT department kind of allocates that stuff to me, and so that's why I do this. This is the way. Really, I only rely on my local VM to flash SD cards, and you can build. You're going to want to build in Ubuntu 18, so that's I keep that per the recommendations. So if I go to, let's see, uname A, you can see that my cloud-based server here, this is a local IP address. I can see that I have an 18.04 machine here. So now this terminal session is effectively Ubuntu 18.04, even though it still says Ubuntu 20. Just to explain, I know people will rage in the comments. Just kidding. I don't think any of my videos have comments yet. But moving on. We're gonna need to get the latest package feed and install some host dependencies now in Ubuntu 18. So we can do that like so. Oh, my caps lock on? There we go. And I think I need that second line. And by the way, this is written such that you can copy and paste these things directly out of the guide. We actually recommend doing that in most cases because, you know, it's too easy to like mistype something in here. Now this step, I want to mention something. This step is often skipped by customers, and it comes up in the support portal. It's because like if you skip this, it's really hard to debug. It's not like clear that this step was the problem, but it will come up as an issue. We recommend running this like so, and when prompted, you're going to select no. What's happening is the system's asking you what shell to use in Ubuntu. It's typically Dash, but that won't work for Yocto. We'll need Bash, and so that's why we select no here. And just so many people skip that. Make sure to do that. Nothing in here is optional. Okay, so now we're going to need some tool chains. I've already done this stuff. Like I said, just copy and paste these line by line. You'll ultimately come up with this tool chain directory like so. And what's in there, you're going to have two cross compilers essentially. Why would I need two, and what are cross compilers? Well, my local machine here, actually the build server I'm using is x86. This is typical of like Windows laptops, desktops, servers, whereas our target system here is obviously a 64-bit ARM architecture. So natively, if I compile things natively here, it will be compiled for x86. It won't run on the target, the phyCORE-AM62. So we need these cross compilers to allow our x86 system to compile software for a 64-bit ARM architecture. And well, in this case, actually, I read that wrong. This is x86, 64. It's the same architecture here, 64-bit. But this one is a 32-bit ARM compiler. This one's a 64-bit ARM compiler. And the reason we need both is because there's so many cores in these application processors these days, and some are like security cores, some are like management cores. You'll notice that there's like 3 different binaries involved during boot just to get U-boot up. And we had a video actually talking about that, if you recall. Those are compiled with these cross compilers depending on the core they're targeting. So Cortex-A's running Linux, those are going to be 64-bit. But then your device manager, I think it's M4 based or Cortex R5 based. Let me know in the comments if you think you know. I think you're going to use this compiler, and so that's all set up by default in the recipes. You just have to make sure that these are available for the build system. So once we have that toolchain installed, we will also need to use this pwd command to get the absolute path to that location. We'll have to supply that to our BSP in a bit so that it knows where it is. Now this step is a good step to do, especially as you go deeper into your development. You're going to hopefully commit your software, all your custom stuff, to some repository to kind of back up those changes. And so you're going to want to get this kind of the de facto version control standard, right, of our industry. So set up Git on your system. I've already done that. Going to skip that step. Moving on, this step. Now this step is very handy because it's just going to force Git to anything that uses the Git protocol for any repository. It'll just change it to HTTPS. And this is because recently there was a announcement from GitHub that the Git protocol was being EOL'd or end of lifed. They're not supporting anymore. And because the Yocto project, it's like, well, this one it's not the bleeding edge Yocto release. It's like Dunfell release, if you're familiar with the Yocto project. So there are some older recipes in there that may not have made this change yet. And so by just having the Git config handle it, you could kind of just continue working with the recipes as they are. It just makes life easier. So run this command. It's not super exciting, but I'll do it. I've done that before. And then now we're going to create the directory to house our BSP. I personally like making this the name of the BSP release. This will help as you try migrating from or keeping up with Vitex releases. That's what we recommend if you want the latest security, the latest kernel, things like this, the latest features. Most stablest releases typically going to be the latest, so yeah, make a different BSP for each one. It's going to make it easier to port things between the two also. So now we're just going to navigate in there, and now we're going to actually start doing BSP stuff. We're not just going to do host setup stuff. This step here, we're going to download this phyLinux tool from our download server here at phyTech. Now, what is phyLinux? It's essentially a repo tool wrapper, if you're familiar with repo tool from Google. It's a way of bootstrapping your build environment, essentially. The phyLinux tool, it's an interactive prompt. You could set up your host, download all the sources for the meta layers that make up the Yocto project. Those themselves contain recipes for like, that are actually build instructions. And so the phyLinux tool just makes it very easy to get all that set up. In order to run it, once we've downloaded it, we'll have to give it executable permissions, and then we just run it with the init argument. So we can just do that together here. Oh, I am typing not so great. It's going to get a knowledge of all the available products. Yeah, it does that based on some default manifest. Now, based on your selection here, right, we want to build for the AM62 platform. So we're going to select number 2. Now it's going to download another manifest that's going to, at this time, right, of recording, there's only one BSP available. So as this product matures, you'll see like a release, maybe a couple a year, and that this list will grow. So depending on your selection here, it's going to, again, download a number of resources, manifests, branches, and then it's going to prompt you for the particular machine that you're going to be building for. So every BSP release will support like a number of SOM configurations with different amounts of RAM, different amounts of eMMC. Maybe the Ethernet PHY is not populated, or it is. At this time, because we're still in alpha stage, we're only really focusing on one prototype system on module. So that's going to ship with 2 gigabytes of RAM. But as this product matures, you're going to see more variations of this product. Maybe there's going to be certain machines paired up with like specific software examples. Like maybe there's a vision related image. Anyway, at this time there's only one, so just select one. Okay, and so now that we have the BSP all set up, what it did was it populated all this stuff. This is all new, right? Yeah, you could see the release notes for the release that you just set up. The juicy bits are all here in sources. So just a quick tour. The meta layers, these are all open source Git repositories themselves, and they come from different locations. So Meta phyTech comes from us. Meta Open Embedded, this is like a core Yocto layer. Also the OE core, OE is Open Embedded. These come from Yocto Project, but Meta Arago comes from TI. So I'm trying to paint a picture here. This is all modular stuff that we can kind of bring together and enable us to build software. We can leverage a lot of open source stuff that's already been made. Meta ARM, so we can get support for a lot of things. Qt, this is a graphics framework, or yeah, I think calling it a framework is appropriate. And then anyway, we could dive into here. Each meta layer organizes recipes, and those recipes themselves are the build instructions. I'm not going to go too far into that. It's a little out of scope for today's video. But okay, so we got the build environment source. Did I do that already? No, I haven't. So what is that? When I do this command, before I run it, let's do a print env. We're going to look at our environment variables here on our host machine. So this is kind of the default environment whenever you create a new terminal. Now watch what happens when I source this build environment like this. So we can see here when we source the environment, the build environment out of the OE core layer here, we are adding a number of new things to the path variable, primarily this bitbake bin out of OE core. There's also scripts in the same location there in OE core. Well, essentially, this is going to, by sourcing the build environment, we're given access now to our main utilities for interacting with the Yocto project, and then going on to build the BSP. That all is kind of handled here with this bitbake utility. Now, before I can really run that, I need to add some information here in the conf/localconf. I should mention, when we source the build environment here, it actually created a new build directory and then placed us in it, and then also copied in some other resources that are going to be utilized through the build, like such as this caching directory and the conf directory, which is where the build configuration is stored. So if we take a look in there, there's a template. We can ignore that, never really look at that. The local.conf is how we actually control the build configuration. And then the BB layers, this is actually listing out the active layers in the BSP. So those would be from the sources directory containing all these meta layers, and the active meta layers must be listed here. Now let's take a look in our local configuration. So that machine that corresponds to a particular SOM configuration from phytech, you can see that that's listed here. This was populated as a result of the phyLinux interactive script and would reflect whatever hardware config you chose there. There's a bunch more stuff that I recommend referencing Yocto Project documentation from. Here at the end, we need to provide the path to that toolchain from before. So if I just like navigate there real quick, again, pwd, we can grab that, copy to the clipboard. I can navigate back with this great build dir directory, or this build dir environment. And actually, that's also one of the variables that got set above by when you source the build environment. So we can navigate around and come right back to the build directory with this easy environment variable. Now let's add our toolchain path here. Easy peasy like so. And now we can utilize bitbake. So right now I didn't provide it like any argument. Let's see what we got to do next here. So there's some other really good things included here in the official BSP guide that talks about what we just did here. There's some other things to consider, like I support multiple products on the same build server. Sometimes I'm compiling BSPs in parallel at the same time, and so it can be beneficial to like limit the number of build resources. So like the number of parallel threads, number of parallel make tasks. We can essentially limit these to maybe like half your total CPU count in order to run two in parallel and not overwhelm your machine. If you do that, you can have your server or Linux host kind of go down as it crunches through the BSP. It's a very task-heavy and task-intensive process, just considering the number of packages that are included in any Linux distribution. So here's the actual target image that we validate here at phytech. So if you want to build a SD card image for your phyCORE-AM62 system on module, we recommend starting here. And this is going to reflect the software that actually is included on your SD card. So if we run this, bitbake will just automatically start parsing all the recipes. And here, there's actually a recipe with this name, and that kind of kicks off everything. And at the end of this process, you'll result in some binaries that can flash to disk and then boot your SOM. So I'm just going to kind of pretend that I went through this process, let that kind of chug along in the background. I'm going to switch tabs and show in a different location what a built BSP would look like. So we bitbaked TSDK default image. Now we should have some new directories. So the downloads directory, this is all the source tarballs that are specified and all the recipes that are active in any given target image, such as the TI-SDK default image. This would include things like Python or Make and GCC. There's recipes for those, and those recipes point to source directories, or source repositories, excuse me. Those source repositories are downloaded as tarballs, and they'll end up here in downloads. They're unpacked in the temp directory here, and so this is where actually all the sources are staged. Then they're compiled, and then once components are built, they are kind of brought together in a deploy directory. So we can take a look in here. This organizes some things. The individual packages can be deployed as IPKs, and you could host these in your own package feed. We'll have a video about that later in this series. And then you can also take a look in the images directory. They're organized by machine. So if there's multiple machines that you're trying to support, maybe you're evaluating multiple SOMs, you'd see multiple directories here as you're building for each one. And then here are the deployed binaries. So really everything in here is reflected in this like kind of master binary. This guy, the .wic.xc, this is a compressed WIC image format. This format can be flashed directly to boot media. So an eMMC device or a removable boot media like an SD card, you'd have to unpack this first and then flash it to a card. And so we'll actually go through that process in a future video.
Alright, well now that we've covered building the BSP, it's time for a coffee break. We will see you guys for the next video.